Hello viewers, Daruna taking you through the story of A-level physics paper 1. And this video we are going to go through the topic of thermodynamics. So this video is suitable for students in both senior 5 and senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. There's a part of heat where 3 questions come from these topics, part of modern physics where 3 questions come from these topics, and the part of mechanics where 4 questions come from these topics. So what is ticked is what has been covered, and what is not yet ticked has not yet been covered. So in this video we are going to go through the topic of thermodynamics, after which we shall go through these other 2. So on this platform you're interested in the calculations, but complete notes are available in the books I recommend. So I encourage you to buy these sets of books. There are 4 for math, 4 for math, and 4 for physics. So you have Mastering A-level Physics paper 1. It has notes of all the parts: mechanics, heat, and modern physics. Then there is Mastering A-level Physics paper 2. It also has all the complete notes. That is geometrical optics, physical optics, electrostatics, electricity, magnetism, and alternating current. Then this one contains solutions for topical questions found in this question bank. So all the 4 books are necessary. That is for physics. Then for math, we also have 4 books. There is Math Paper 1 contains complete notes, Math Paper 2 contains complete notes, then a topical question bank for UNEB and also termly past papers. This termly contains beginning of term exams, mid-term, end of term, mocks, and UNEB past papers with their marking guides. So these 4 books are also necessary in case you do principal mathematics. For those who do subsidiary mathematics, it is only 1 book. And for copies, contact the author on any of these 2 and on this contact. It's also on WhatsApp. So now we can start our topic of thermodynamics. So this part of thermodynamics, it's a science which deals with the relationship between heat and work done by a gas. So this is what we are interested in: heat and work done by a gas, by considering the thermal effects using quantities like pressure, temperature, volume, and internal energy. So internal energy of an ideal gas is the kinetic energy of the thermal motion of its molecules. And its magnitude depends on the number of molecules and the temperature. So we have what we call the law of thermodynamics. So gas changes involve change in pressure, temperature, volume, and heat quantities. And these changes are governed by the law of thermodynamics. This law can be written mathematically, and it states that the total energy in a closed system is always constant. So the word total energy has to be seen, closed system must be seen, and the word constant has to be seen. So the word closed system means that the energy is conserved in any transfer of energy from one form to another. So mathematically, you can write that law of thermodynamics. So shall I give an example that when a gas is warmed, it expands, and the heat given out is delta Q. So delta Q denotes heat given out. Appears partly as an increase in its internal energy. So delta U will denote internal energy, and partly as the energy required for the external work done. So delta W denotes external work done. Therefore, mathematically, we shall say that delta Q will be equal to delta U plus delta W. So heat given out is equal to internal energy plus work, external work done. So this is our interest in the calculations. So you already know what that means. Delta Q, heat supplied, delta W, internal energy. So delta U is the internal energy, and delta W is work done. So we want to code the formula for each, this delta Q, delta U, and delta W. Therefore, you come and say that if P is the pressure applied by the gas and delta V is the change in volume, the external work done by the gas will be given by pressure times change in volume. So we have now got the expression for delta W. And that can help us to do these questions. Question 1 came from UNEB 2001, paper 1, question 7D, and it says, calculate the work done against the atmosphere when 1 kilogram of water turns into vapor at atmospheric pressure of this. Here they say that the density of water vapor is this. Remember we said work done is pressure times change in volume. So they have told us that water turns into vapor. Therefore, we need to get the change in volume. The good thing, we have density and we have mass. So shall remember that volume is mass over density. Therefore, for water, mass is 1 kilogram and density for water is a constant. It is 1000 kilograms per meter cubed. So you come up with 0.001 meter cubed. What about water vapor? Water vapor mass is still 1, but density is 0.598. Therefore, the volume will be 1.67 to 2 meters cubed. Now that I've got the two volumes and I know the pressure, I can get the work done. So work done against atmospheric pressure will be P times change in volume. P is here and change in volume is here, which gives you this as the work done. And that's what they wanted. Then question 2 came from UNEB of 1993, paper 1, question 5E, and it says, an ideal gas of volume 1 liter, so this S shouldn't be there, at STP, STP is standard temperature and pressure, expands at constant pressure to a volume of 3 liters. Calculate Roman 1, work done by the gas, and Roman 2, the final temperature of the gas. So a good thing, they've told us it is an ideal gas, so it obeys the gas laws. So volume 1 liter will be equal to 1 exponent negative 3 meters cubed. Then 3 liters is 3 exponent negative 3 meters cubed. So I've got the two volumes, I need pressure. So at STP, pressure is atmospheric pressure, which will be this. And temperature is this, which is 273 Kelvin. So these values are constant. Each time you see this word STP, standard temperature and pressure. So standard temperature will be 273 Kelvin and pressure will be atmospheric pressure. Always. So now that I know the pressure, I know the two volumes, I can get the work done. Pressure times change in volume. So pressure is here and change in volume is there. Use a calculator to come up with 202 joules. That was Roman 1. What about Roman 2? Roman 2, they want the final temperature of the gas, so we shall use the gas laws. So since pressure is constant, then we shall use Charles's law, which is V over T is a constant. So V1 over T1 is equal to V2 over T2. Then come and substitute for V1 and T1, V2, T2 is what we want. So make T2 the subject, and that will be the value they want. So now that we have seen how to use the formula for external work done. But remember, at first we had the law as dQ equal to du plus dw. So the previous examples we have done have been helping us to get dw, which is external work done. But how do you get internal energy or heat supplied? That is what we want to see. So for you to get these formulas, you need something called molar heat capacity. So let's first talk about this term called molar heat capacity. Now this molar heat capacity is in two parts. There's what we call molar heat capacity at constant pressure and also molar heat capacity at constant volume. Each time you see a symbol Cp, it means molar heat capacity at constant pressure. So how is it defined? So it is defined as the quantity of heat required to raise the temperature of 1 mole, not this word, 1 mole, of a gas by 1 Kelvin. You can say 1 Kelvin or 1 degree Celsius at constant pressure. Remember, it was Cp. Cp means constant pressure. So when you're defining, you have to end with the word constant pressure. That means that dQ at constant pressure is equal to N times Cp times change in temperature, where N is equal to 1 because they said 1 mole. Then change in temperature is 1 Kelvin because that's what they said. So each time you see constant pressure, just know this is the formula for dQ. Then another form of molar heat capacity is one which is Cv, and that is molar heat capacity at constant volume. So the definition is somehow similar, but this is constant volume. So it will be heat required to change the temperature of to raise the temperature of 1 mole of a gas by 1 Kelvin at constant volume. So the keyword is constant volume and constant pressure. Otherwise, the rest are somehow similar. That means that the Q at constant volume is given by NCV. So here it was Cp. Here it is Cv because it is constant volume. So don't forget this. So these symbols are standard. When you write Cp, it means molar heat capacity at constant pressure. When you write Cv, it means molar heat capacity at constant volume. So now that we know that, we need to get the relationship between Cp and Cv. So all this is going to help us to solve some calculations. So we need to know these terms. So now that we know what Cp is and what Cv is, we can get the relationship between the two. And along the way, the relationship will help us. So we shall consider 1 mole. 1 mole means N is equal to 1 because N denotes number of moles. Consider 1 mole of a gas warmed through 1 Kelvin, that means change in temperature is 1, at constant volume. Because volume is constant, it means there is no change. That is why V is constant. The heat required will be given by dQV equal to, remember this is the law of thermodynamics. So when it is constant volume, we put dQV. If it was constant pressure, we would put dQP, as we shall see along the way. And remember, we saw the formula for dQV. It was NCV, change in temperature. Then you already saw earlier the formula for external work done. It was pressure times change in volume. So now what we are going to do, we shall remember that N is equal to 1, delta T is equal to 1, and delta V is equal to 0. When we remember that, we shall come and write, substitute for N, delta T, and delta V. Then you remain with CV is equal to delta U. Remember, delta U is internal energy. That was when volume is constant. What about when the pressure is constant? So shall also consider 1 mole of a gas warmed through 1 Kelvin at constant pressure. So the heat is given by, now here, remember here it was dQV, now we shall use dQP because pressure is constant. Then we know that this N is 1 and delta T is 1. So come and substitute for dQP and also external work done. N is that, T is that, volume, there is a change in volume. So V1 is and V2 are the initial and final volumes. So that means that when I come, first this one, when I put it inside, I'll come up with PV2 minus PV1. And this one, I'll remain with only CP. And this one, we already saw that the delta U is equal to CV. So I come and substitute for delta U here to come up with this. Okay. Then I remember from the gas law that PV1 is equal to RT1 and PV2 is equal to RT2. Now, usually it is PV equal to nRT. But now we are not putting the N. I think we can see it is just RT. Why? Because we have already said that N is equal to 1 mole. So 1 mole means 1 times RT, which remains RT. So that's why you're not seeing N here. Otherwise, the ideal formula would be PV equal to nRT. So now we're going to substitute for PV1 and PV2 to come up with this. From that, R is constant, so factorize it out. And this one denotes change in temperature. And we say that change in temperature is 1 Kelvin. So I'm going to substitute for T1 minus T2. I'll put there 1 to come up with that. Then I'll rearrange to come up with CP minus CV is equal to R. So always remember that CP is bigger than CV. And there is a reason for that, but that reason will be got in the book. For now, we are interested in what can help us to attempt the calculations. Remember, on this platform, we are interested on the calculation bit of it. But there is more on this topic, and that more will be found in the books. That is why I encourage you to buy those books. Don't only rely on the YouTube. So YouTube will help you in the calculations, but other theoretical part will be found in the books. So this formula is very vital. We are going to use it along the way. And it is the relationship between CV and CP and CV. So when they ask you to derive the relationship between CP and CV, you have to derive up to this part. Remember, we have been dealing with molar heat capacity. What if they use the word specific heat capacity? There we use small letters. I think we realize here, these are capital letters. Capital letters mean molar heat capacity. Then small letters or lowercase letters mean specific heat capacity. But the rest is the same, meaning that it will now be also Cp minus Cv over small r. Here we use capital letters, so we use small letters. Now, what is r? That small r, we get it from Pv is equal to mRT. So that if you know the mass, you can get r, small r from the gas equation. So with those formulas, we shall go through these questions. Question 1 came from U.A.C.E 2014, paper 1, question 5b, and says the specific heat capacity of oxygen at constant volume is this. Okay, and its density at standard temperature and pressure. So standard temperature and pressure means STP is this. Calculate the specific heat capacity of oxygen at a constant pressure. So here, what was given is called CV. Now they want CP. So shall come and quote the formula. We're using this formula because they said specific heat capacity. If they had asked molar heat capacity, we would have used PV equal to capital RT. Because they're specific, we use small letters here. Then you come and substitute. Rearrange this, put this on this side, because this one will give you the density which is already known. So come and substitute. Standard temperature and pressure means temperature is 273 and pressure is atmospheric pressure. Then M over V is the density. And R, we don't know it. So let's first get R, small r, it is that. After getting small r, we shall remember the relationship between Cp and Cv in small letters. Then shall quote, because with this one we know Cv. Substitute for Cv and also the r you have got. Then make Cp the subject. And that's what they wanted. Then question 2 came from U.A.C.E of 2010, paper 1, question 6d, and says 10 moles of a gas initially at 27 degrees Celsius are heated at a constant pressure of this, and the volume increased from this to this. Calculate the increase in internal energy, that is delta U. Assume Cp, these are capital letters meaning it denotes molar heat capacity at constant pressure. Okay. So number of moles, we shall first interpret the question. Number of moles are 10. Then the temperature initially was 27 degrees Celsius, convert to Kelvin. Then the pressure is here. And volume, from initial volume is that, final volume is that. So at constant pressure, we use Charles's law. V over T is constant. Then you can come and substitute V1 and 2 over T1, V2 over T2, which we don't know. Then make T2 the subject. So that we have now got the temperature. We have now got the final temperature at this volume. But remember the question wants increase in internal energy. So by conservation of energy, we shall use the QP because they talked about constant pressure is equal to delta U plus delta W. And we already know that the QP is this, NCP delta T, delta U, and we already know that delta W is P times change in volume. So we shall come and make du the subject. it gives us this, which is here, and this, which is here. Then we come and substitute. Substitute for N, number of moles, substitute for Cp, which was given, substitute for T2, T1, P, V2, V1. And then use a calculator to come up with the answer they wanted. And that would be the internal energy they wanted. Then question 3 came from UNEB of 2008, paper 1, question 6C, Roman 2. And it says, nitrogen gas is trapped in a container by a movable piston. Okay. If the temperature of the gas is raised from 0 degrees Celsius to 50 degrees Celsius at constant pressure of this, and the total heat added is this, calculate the work done by the gas. Then they give you that molar heat capacity of nitrogen at constant pressure. So Cp is 29.1. Then also the ratio of Cp over Cv is 1.4. So shall come and say that, first of all, heat supplied. Heat supplied is the Q. It is the QP because they talked about constant pressure. Then change in temperature is that. So I think you realize here, it was in degrees Celsius, but our answer is in Kelvin because it is the same. A change in temperature in degrees Celsius is the same change in temperature in Kelvin. We already know that the QP is equal to NCP, change in temperature. So come and substitute for the QP, and we don't know, Cp is that, change in temperature is that. So the number of moles will be that. After getting the number of moles, we can come and remember that Cp over Cv is equal to 1.4. That's what was given. And the good thing, we know the value of Cp, meaning I can get the value of Cv by making it the subject, which will be that. But remember, the question wants work done by the gas. So by conservation of energy, the QP is equal to du plus dW. So make dW the subject, I'll get the QP minus internal energy. So the QP, it was already given. Then internal energy is NCV delta T. So N is that, CV is that, and delta T is that. So use the calculator and that will be the work done. So now we have looked at the law of thermodynamics and you have seen how you can get internal energy, external work done, and also, so I've seen how to can get the internal energy, how you can get external work done, and also how you can get the heat supplied at constant pressure and also heat supplied at constant volume. Okay, now what we are going to look at are the processes. The process can be change in volume, change in pressure, change in temperature. So the process we can look at, and the process can be reversible or irreversible. Now let's first define these two terms and give examples of each. So they can talk about a reversible process or an irreversible process. Now what is a reversible process? Remember, we have said that changes will be in volume, temperature, and pressure. So reversible means it can go back to the original state with negligible changes in volume. For example, if, for example, the volume initially was 5 liters, then it increases to 10 liters. Then you make it to undergo a reversible change and it goes back to 5 liters. that means it is reversible. But if you cause it to go back and it goes back to 4, it means it is irreversible because it cannot go back to the original value. So that's why the definition comes in that a reversible process is one that can take place in the reverse direction through the same, note this word, same values of pressure, volume, and temperature in small changes or steps. So the word same is vital under reversible processes. And as some of the examples can be melting of ice, the volume can remain the same. Another one can be expansion of a gas by a frictionless. Because if there is some friction, some energy will be wasted as in form of heat. So it has to be frictionless piston. That is what we call a reversible process. What about an irreversible process? So an irreversible process is one which cannot be made to go in the reverse direction under the same conditions causing it. So it cannot. That's the key word. And some of the examples can be 1. Burning of kerosene, or what we call paraffin. It cannot because it will go off. You can't make it go in the reverse process. Once it burns, it has burnt. You can't bring it back. Then expansion of a gas by a piston against friction. The energy which will be lost due to friction will have been lost. You can't again bring it back. But for here, ice, you can turn it to what? It goes to liquid and can go back to ice. But here, kerosene, once it burns, it has burnt. So those are the differences between reversible and irreversible processes. Now, once we know those ones, we are going to also go through, we also need 2 terms. Actually, these 2 terms are the ones we shall use in the calculations. One is called one is called isothermal process, another one is called adiabatic process. So we shall look at both of them, then after which we shall go to the calculations. Iso means same, then thermal means temperature. So when they say isothermal, what should come to your mind should be that temperature is constant, but the rest can change. Remember, the changes we're interested in are pressure, volume, and temperature. So when they say isothermal, it means pressure and volume can change, but temperature must remain constant. Therefore, an isothermal process is a change in pressure and volume of a fixed mass of a gas at constant temperature. So isothermal temperature must be constant. Then we need to look at some formula, to derive some formulas. So formula for work done by a gas during isothermal change. So when temperature is constant, how can we get the work done by a gas? So you consider n moles of a gas enclosed in a gas container of cross-section area capital A by a frictionless piston. Remember we said frictionless piston initially at equilibrium. So when they say the word frictionless, it means isothermal process is reversible. Frictionless piston initially at equilibrium at point X as shown below. So we shall need to make a simple sketch for us to easily derive the expression we want. So this is a gas container and it has a frictionless piston. So when the piston is pulled outward, the volume will increase because initially it was from here to here, now it is now from here up to here. So volume will increase. So inside there is force due to the pressure inside the gas, and outside there is external force due to external pressure. So the force F gas exerted by the gas inside the container due to the gas pressure is given by cross-section area times pressure. Okay, but when it's at equilibrium, it means that forces to the right are equal to forces to the left, meaning that F gas is equal to F external. Therefore, F external is equal to Fp. Now, if the gas expands through a small distance delta x, so small that the gas pressure P remains constant, the small external work done will be force times distance, which is Fp times delta x. But small change in volume dV, delta V is equal to cross-section area times delta x, which is change in length. Therefore, you come and remember that external work done is pressure times change in volume. So you shall come and substitute. Therefore, total work done W when the gas undergoes a reversible isothermal expansion at a temperature T such that its volume changes from V1 to V2 is given by that. So this was small work done, but when we come to total work done, we put now integration from V1 to V2 of P, then delta V becomes dV. So now we need to integrate. We shall remember that from PV equal to nRT, P is equal to nRT over V. Therefore, work done is equal to nRT over V dV. Now this is constant, so pull it out to give you that. Then integrate 1 over V to give you natural log of V. So after integrating, we shall substitute limits. So substitute this here minus this to give you, remember, in natural logarithms are like logarithms. When I substitute for V here, I'll come up with ln V2, then minus ln V, sorry, this is V2, this is not a power, it is V2 down here, and also ln V1. But because it is like logarithms, so ln V2 minus ln V1 is the same as ln in brackets V1, V2 over V1. So that's where this one is coming from. So that will be the expression for work done by an isothermal process. So each time you realize that temperature is constant, remember to use this formula. So if the work value W you have got in the calculation is positive, it implies that work is done by the gas. But if W is negative, then work is done on the gas, so not the difference. Therefore, and this, when it's negative, it means there was a contraction. When it's positive, it means there was an expansion. So now the second process is called adiabatic process. So an adiabatic process, this one, everything changes. Remember, the changes we're interested in are temperature, pressure, and volume. For isothermal, pressure and volume would change, but temperature would remain constant. That is isothermal. When it comes to adiabatic, all the three change. So adiabatic process is a change in temperature, pressure, and volume of a fixed mass of a gas, but the condition is that no heat is allowed to enter or leave the gas. That means that dq is equal to 0. Okay. And examples for adiabatic change can be sound transmission in air, a bursting tire or a ball, inflating a tire or a ball, compression stroke or power stroke of a 4-stroke cycle engine. So for isothermal, we have seen what we should realize that for isothermal, we have seen the formula for work done, and also isothermal obeys Boyle's law of PV equal to constant. But when it comes to adiabatic, it changes a little. So we need to see this equation for adiabatic process. So the expression rating pressure and volume for an adiabatic process is given by that. Remember, for isothermal, we said it obeys Boyle's law, so it is just PV equal to constant. But when it comes to adiabatic, it becomes PV to power this symbol. Now, this symbol is the ratio of Cp over Cv. So that is the difference between adiabatic and isothermal. For adiabatic, it is PV equal to constant. But isothermal, it is PV raised where V. Now, this power is only on V. Don't confuse the two. The power is only the V, and this power is the ratio molar heat capacity at constant pressure to molar heat capacity at constant volume. Now, that is when I'm given in terms, remember, for adiabatic, all the three change: the pressure, volume, and temperature. Now, what if I want to get the relationship between pressure and temperature? It means that in the first equation, I will eliminate V using this formula, that PV is equal to N is equal to RT. So I'll come and substitute for V to come up with this. And when I use the rules of indices, this is what I'm going to get. I'm going to get R to P, which is, there is P, then which is here, P to power 1, then R to power the ratio, then T to power the ratio, and P. Now this P is down, that means P to power negative ratio, which gives you now P to power 1 minus this ratio, molar ratio. So this is just applying rules of indices to come up with that. But now, because this one is a constant, it implies that the whole of this will become a constant. Therefore, we come up with a formula that P to power 1 minus ratio, 1 minus the molar ratio times T to power molar ratio equal to a constant. So this is a formula for when I want to get the relationship between pressure and temperature. Now, what if I want to get the relation between temperature and volume? It implies that from the first equation here, in this first equation we wrote here, we are going to make P the subject, replace P, because we want to eliminate it. So P is equal to RT over V. So come and substitute for P. You'll come up with this. Now C means constant. Constant over R, everything is constant. So we'll come up with this. So those are the three equations for an adiabatic process. For isothermal process, it is gas laws. PV equal to, it is actually Boyle's law because temperature is constant. So when given a question, find out, is the change adiabatic or isothermal? If you say change in temperature, just know that you are dealing with adiabatic process. But if you see temperature remaining constant, then just know that you are dealing with isothermal process. Now, just like isothermal process, even in adiabatic process, we need to get the formula for work done by an adiabatic process. So we shall derive it by considering n moles of a gas undergoing a reversible adiabatic expansion from volume V1 to V2 such that its temperature changes from T1 to T2. So the work done will be given by this. So this is the law of thermodynamics. It's what we're going to use. So you should remember that for adiabatic process, dQ is equal to 0. I think you remember that from the definition. So I'm going to substitute for dQ equal to 0 and internal energy, substitute with NCV, change in temperature. Therefore, W can be got by integrating this. Now, integrating from T1 to T2, and dt delta T becomes dt. So when I integrate, first of all, these ones are constants. When I integrate, I'll come up with T and substitute limits to come up with T2 minus T1. So from PV equal to nRT, it implies that T is equal to that. Therefore, actually this is one formula for work done by an adiabatic process in case you are given temperature. But if temperature is not given, is not known, then we have to get the second formula by eliminating T. That's why you're saying T is equal to PV over nR. So come and substitute for that T here and this T here. When you do that, you shall come and get this. And from this, we can remember that first remember that Cp minus Cv is equal to R. So meaning you can replace it here. Okay, now after replacing, what next? Here what we have done, we have split the numerator by getting this over this to give you this, then this over this to give you 1. Then remember that we said this is the molar ratio of at constant pressure to constant volume. So I'm going to replace it with that symbol. Okay, then from there, so this symbol is called gamma, in case you've been wondering what it is called. But here in this topic, we shall refer to it as the molar ratio at constant pressure to constant volume. So making W the subject, I'll come up with this, and I can replace PV with nRT to come up with this. Then in the end, this denotes change in temperature. So this formula is when temperature is not given. But if temperature is given, then you can use this, or the first one we had seen in the previous slide. So that is the formula for, we have now looked at the formula for work done by an isothermal process, work done by an adiabatic process, equations for an adiabatic process, and equations for isothermal process. So the equation for isothermal process is called Boyle's law. As simple as that. So next, because some questions, they can tell you to sketch a PV curve. So you need to know how an isothermal curve looks like and how an adiabatic curve looks like. So an isothermal curve is like I said, Boyle's law. So it is exponential, but temperature has to be constant. So along this curve, volume is changing with pressure, but temperature is constant. Even this one, volume is changing with volume is changing with pressure, but temperature is constant. And the higher temperature is above the curve. For example, if T2 is bigger than T1, it will be above. And then a smaller temperature than T1 will be below T1, like that. Now that is isothermal curve. What about adiabatic? Adiabatic, all the three are changing. Here, it is pressure and volume changing. Here, so pressure and volume changing. But for adiabatic, all the even temperature should change. So we shall connect from one temperature to another temperature. And that will be adiabatic curve. So if you see a change in temperature, then there is adiabatic process. So there's a difference between isothermal curve and adiabatic curve. So now that you have seen the formulae and we have also seen the curve, we can go to the calculations. So now that you have looked at the formulae for isothermal process and the ones for adiabatic process, and also the isothermal curve and adiabatic curve, it implies that we can now go through these questions. So question 1 will be from UNEB 2016, paper 1, question 6C, and it says, a gas at a temperature of 17 degrees Celsius and pressure of 1 × 5 pascals is compressed isothermally to half its original volume. It is then allowed to expand adiabatically to its original volume. Sketch on a PV curve the above processes. I think let's start with Roman 1. So Roman 1 shall come and draw the axes of volume and also of pressure. Then we have the volumes. There is original volume and half the original volume. Then the corresponding pressures, we need them. Okay, so first of all, we shall also need the isothermal curves for the two different temperatures. Okay, so initially the volume was V and the pressure was 1 × 5, meaning it is initially at this point. Then they said that it is, let's look at the question. They said compressed, meaning volume reduced to half the original volume. So you come here and say that half the original volume is here, and to correspond to a pressure P2, which we don't know yet. So the curve will be from here up to here. So let's come and draw it. So that is the isothermal compression. Then from there they said it expands. Let's go back to the question. It is then allowed to expand adiabatically to its original volume. So expanding adiabatically means there is a change in temperature. So to move from this point to this point, then to this point, like that. Temperature has to change. It was initially T1, now it is T3, corresponding to P3. So we shall come and draw that expansion. So basically that is what they wanted in Roman 1. Roman 2, they said, if the specific heat capacity at constant pressure is 2100 joules per mole per Kelvin and at constant volume is 1500 joules per mole per Kelvin, find the final temperature of the gas. So these ones will help us to get the lambda or the molar ratio. So you come and say that initially T1 was 17 degrees Celsius, convert to Kelvin, P1 was 1 exponent 5 pascals. Then after isothermal compression, V was V, then V2 is now half V, and temperature is still the same because they said isothermal. Then after adiabatic expansion, T, we don't know it, but V is the original volume, which is now V. So remember the question wants final temperature. So shall use the formula which has volume and temperature for adiabatic process. And that formula, so before that we need the lambda, we need gamma, or the molar. Now this time it is specific ratio of specific heat capacities. I think realize we are using small letters because these are specific heat capacities. So this ratio is 1.4. Then you can quote the formula. T2 V2 to power gamma minus 1, then T3 V3 to power gamma minus 2. So T2 is this, and V2 is that. Then you substitute for gamma. T3 we don't know, V3 we know, substitute for gamma. Now from there, we need to make T3 the subject. So T3 will be equal to 290 times 0.5 to power 0.4. Now where did it come from? First of all, it came from here. So if I bring this one, first of all, this one is 0.5 V divided by V, which is this. Everything is raised to the power 0.4. 0.4. So this V will cancel and remain 0.5 to power 4, which is there. And using a calculator gives you that as the temperature, and that's the final temperature they wanted. Then question 2 came from UNEB 2005 paper 1 question 6b, and it says an ideal gas is trapped in a cylinder by a movable piston. Initially, it occupies a volume of 8 exponent negative 3 meters cubed and exerts a pressure of 108 kilopascals. The gas undergoes an isothermal, this is what we want, isothermal expansion until its volume is 27 exponent negative 3 meters cubed. Okay, it is then compressed adiabatically to the original volume of the gas. Original volume was this. Calculate the final pressure of the gas. So let's start with the Roman 1. Final pressure of the gas. So shall come and say that initially V1 is that and P1 is that, which is that in pascals. Then after isothermal expansion, V2 is this, and P2 we don't know it. So shall use Boyle's law, which is P1 V1 equal to P2 V2. Substitute and make P2 the subject. This will be the value of P2. After getting P2, we can now go to adiabatic compression. For adiabatic compression, V3 was the original volume, which is now that. P3 we don't know it, and the ratio we know it. So we need to get the adiabatic equation for P and V. I think you remember it. So the relationship is that PV to power gamma is constant. So we can get this. Then we substitute by making P3 the subject to come up with this. Then substitute for P2, for V2, V3, and the gamma to give you this as the pressure. So that is the pressure. That was Roman 1. They wanted only pressure. Then Roman 2, sketch and label the two stages on a PV diagram. So the good thing, we know initially P is here, V is here. Then after the expansion, P is here, V is here, and after the compression, V is here, P is, we have got it. Therefore, we can come and sketch. So first draw the axes and label them. Volume and pressure. Then from there, you put the values, only the values you have got, P1, P2, P3, like that. Then you draw the isothermals, isothermal curves for two different temperatures because there was an adiabatic compression. Then initially, V was this and P was this. So we have that point. After the expansion of isothermal, V was this, P was this, like that. Isothermal means constant temperature, therefore it will move from here up to here. So let's draw that curve. Next was adiabatic compression, and P was this and V was this, which gives you this point. So it will move from here up to here. I think you notice there's a change in temperature, meaning it is now adiabatic. And that's what they wanted. So that is Roman 2, that's what they wanted, so you're done with the question. So we can now go to question 3. Question 3 came from UNEP of 1995, paper 1, question 6D, and it says, a gas initially occupying a volume of 1 liter at 273 Kelvin and 1 exponent 5 pascals is compressed isothermally to a volume 0.5 liters. It is then allowed to expand adiabatically to the original volume. Roman 1, find the final temperature and pressure of the gas. So let's first get that. So initially, P is that, V is that, and temperature is that. Then after isothermal compression, P is not known, V is known, temperature is known. Isothermal means temperature is constant. Therefore, we can use Boyle's law to get the value of P2, which is that. What about after adiabatic expansion? V is known because it went back to 1 liter. T is not known, the gamma is known. So if I use P and V, I'll come up with the value of P3 as that. Then if I use T and V, I'll come up with the value of T3 as this. And that's what they wanted. They wanted final pressure and final temperature. Then when we go to Roman 2, they want you to indicate the process on a PV diagram. So you come and draw the axes, volume, pressure. Then put the values we shall use to sketch. Then draw the isothermal curves. One at that temperature, another one at that temperature. Then initially we have V as 1 and P as this. So we have this point. after the compression, which is isothermal, V was this and P was this, still on the same temperature. So we shall draw that isothermal compression. So for adiabatic expansion, the volume is this and the pressure is this. Therefore, we need this point. Therefore, we shall draw from here up to here. So let's do that. And that is what they wanted. Now we shall go to question 4. So question 4 came from UNEB of 1997 per 1 question 6b. And here it is edited because we added on these Romans for you to know, because in the previous 3 questions, the questions were only about final temperature, final pressure, and the diagram. But we've not yet done a question on work done for isothermal and for adiabatic, yet you need them. So that's why we called it edited, because we added on this for you to easily know how to calculate work done for adiabatic process and also for isothermal process. So it says that a vessel containing 1.5 exponent negative 3 meters cubed of an ideal gas at a pressure of 8.7 exponent negative 2 pascals and a temperature of 25 degrees Celsius is compressed isothermally to half its volume and then allowed to expand adiabatically to its original volume. Calculate the final pressure and temperature of the gas. Take the ratio as 1.41. So you shall come and say that initially P1 is that, V1 is that, T is that, T1. Then after isothermal compression, V2 is that, T2 is the same as before, P2 we don't know it. So we shall use Boyle's law to get the value of P2. So P2 will be that. Then after adiabatic expansion, V3 is now that original volume, T3 we don't know, P3 we don't know, and the ratio we know. So you come use PV and then substitute to get the value of P3, which should be that. Then for temperature, we shall use T and V and then substitute to get the value of T3, which will be that. And that's what they wanted in Roman 1. Then for Roman 2, they want you to sketch the PV curve graph for the whole process. So draw the axes and label them. Then put the values of interest, volumes, and also for pressure. Then draw 2 isothermals, one at the temperature of 224.3, another one at the temperature 298 Kelvin. Then initially volume is this and pressure is that, so you have that point. Then after the isothermal compression, volume is this and pressure is this to give you that. So it is isothermal, so it will be along that curve. Therefore, you shall come and draw it. Then for adiabatic expansion, the final pressure is this and volume is that, which gives you this point. So to move from here to here, because there is a change in temperature. So we shall come and draw that, and that will be the PV diagram they wanted. Roman 3, they want work done during isothermal process, and Roman 4, work done during adiabatic process. So you need to remember the formula for work done during isothermal and also during adiabatic. So for isothermal, the formula is this. Here you can put I think remember we had put RT, nRT. You can either put nRT or PV depending on what is given. So yeah, you have pressure and volume, that's why you're using PV. So PV ln V1, V2 over V1. So come and substitute. So this one, ignore it. Ignore this line. This is the correct line. So come and substitute for P V V1. Sorry, V2 V1. You'll come up with a negative. And I think you remember we said when there's a negative, it means there was an isothermal compression. So that's why there's a negative. Then work done during adiabatic process. The formula and substitute. So P3, V3, P2, V2, and gamma. So use the calculator, you'll come up with this as the work done for adiabatic process. And basically that's what they wanted in this question. Then question 5 came from UNEB of 1996, paper 1, question 6C. It says, an ideal gas at a pressure of this occupies a volume of this at 47.5 degrees Celsius. The gas expands adiabatically to a final pressure of this. The ratio of the specific heat capacity at constant pressure to that at constant volume is this. Calculate Roman 1, the number of moles of the gas. So let's start with Roman 1. So initially we have mass as that to change to grams, then molar mass, which is 28 grams per mole. P1 is that, V1 is that, and T1 is that. You convert to Kelvin. So for an unideal gas, PV is equal to nRT. So I'll come and substitute for P, for V, for R, and for T. So now I can get the value of N by making it the subject. And that'll be the number of moles they wanted. Then Roman 2, they want the final volume of the gas. So remember, it expanded adiabatically. So after adiabatic expansion, we know P2, we don't know V2, we don't know T2, and we know the ratio. So shall come and code, first of all, if I want to get V2, I'll code the formula for P and V, then substitute, and then make V2, look for ways of making V2 the subject. So here it means that I'll take this power the other side. That's why we see a 1 over 1.4. It is a law of indices. So we'll come up with this as the volume. Then for Roman 3, they want the final temperature of the gas. So we shall code the formula for T and V, then we substitute to get the value of T. And that will be the final temperature they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on vapors, still under the section of heat. So if you're not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.